Okay, welcome everybody to this session on Thursday morning, so tomorrow is the last day, unfortunately. So today's speakers are Sofia Imperatore from University of Florence and Alen Kushova from University of Pavia. And they will give a short course, long course, let's say it's 4 hours, but we will have 3 breaks for sure, because it will be divided into 4 parts, and it is about spline function for shape learning and PDEs approximation. So please.
Thank you very much for the introduction, and I would like to thank also the organizer to give us the chance to hold this course. And in particular, I would like to stress that me and Alen didn't know each other before YAMC, but we were given the opportunity to get in contact and to prepare this course together, since we are working not on the same research topic, but let's say with the same instruments, that is the splines and the spline functions, with different applications. Yeah, thank you. So this is the outline. So Alen will introduce the B-splines, which are these functions we are using. Then I will talk about B-spline curves in a computer-aided geometric design environment. Then Alen again will introduce you to the wonderful world of isogeometric analysis, and I will conclude with some other application of computer graphics and an extension to the adaptive setting. So, Alen, please.
Thank you very much. So thank you all for coming, and let us start with a very simple introduction of what B-splines are. Okay, how we define them, and let us see some particular properties they have. So, first of all, let us start with the univariate case. We select an interval AB, subset of R, and we fix a polynomial degree P, and K, we call K P plus 1 the order of the polynomial, and B-spline basis functions will deal a polynomial basis, and we call by Mi the multiplicity, in the sense of multiplicity of knot vectors, and some this Mi should vary from 1 to the order K. What are knot vectors? We have an extended, let us call it extended knot vector, just simply a set of points in the real line, ordered as you can see below, where they vary from, let us start counting from 0 until n plus k. So we have n plus k plus 1 knots. The k minus 1 knot is the left side of the boundary of our interval, okay? And the other extreme is the knot Tn plus 1. Okay? We have an ordering, we have a set of knots, we can admit repetition of these knots, repetition at must Mi must be lower than k times. And this is the structure of a typical knot vector. We call this capital T, sorry, not capital, but boulder T, the knot vector. And from this knot vector, we can define the basis, the polynomial basis of these splines functions. And they will be, since we have n plus k plus 1 knots, we will see we will have n plus 1 basis function. N plus 1, we're starting counting from 0. Okay? Some of the people start counting from 1, and they have a similar notation but let us focus on these topics. Okay? How they are introduced? We have, in order to define the B-spline functions, a recursive formula, thanks to Cox-Gore, to mathematicians, of course. I don't know pretty much about the history, but this is an important recursive formula. This is not the principal way to introduce B-splines, but is the easiest one, and from the computational view, the preferred one. Okay? You, for order k equal 1, that means degree 0, so constant functions, let us say. The definition is that each of the basis functions is like, as you can see, piecewise constant in the interval. This is called ti plus 1 is called the knot span. Okay? So each of these basis functions is 1 over a knot span, a single knot span, and 0 otherwise. Okay? And on the right, you can see the shape, of course, of these piecewise constant functions. Thanks to Cox-Gore recursive formula, for greater orders, so greater degrees, we have a recursive formula that is the B-spline, the ith B-spline of order R, is defined as a linear combination of the B-splines of order R minus 1. Okay? We have some weights and a linear combination of just 2 of the previous order B-splines, and the weights are such that this is the ratio whenever t is lower than the point when it starts the support of this B-spline. Otherwise, it is 0. Okay? This is a simple definition. Let us give some examples. Okay? Fix a knot vector t. For example, starting from 0, 0, 1, 2, 3, 4, 5, 6. Okay? We are not repeating knots in this case. We also fix an interval AB, and this, for example, for order k equal to polynomials, it will be T1, T5, according to the previous introduction of knot vectors. Okay? This is our interval, the domain where we want to define the basis functions of order k equal to, so polynomial degree 1. Okay? And what we have, we will have 5 basis functions of order 2. This is thanks to the recursive formula. Let us vary I from 0 to 4, so 5 basis functions. This is generally the expression of the ith basis function of order k. Okay? And let us see an example. Some computation. At the very beginning, the first one is expressed like t in the knot span from 0, 1, and 2 minus c in the knot span from 1 to. Okay? And here we have the shape of the basis function of order k equal to. As you can see, they are exactly the head functions that you must have seen or may have seen during numerical analysis courses, okay? For polynomial approximation. Well, this is the first basis function, the head function. This is the shape of the second one, okay? So we moved it a little bit on the right, and so on. We can go on, the third one, fourth one, the fifth one. And according to the recursive formula and the weights, we have this expression, okay, explicit expression. Very nice. This is an overview of all the basis functions we have introduced. Remember, the interval we are considering AB, where we define the basis function, is given by the knots T1, T5. So we are in the interval 1, 5, okay, and they will span, okay, we will see it later, a polynomial space over the interval AB. Okay, but just one step at a time. Some other examples, because maybe head functions are simple. Still, again, fix this not vector. Now, let's take k, the polynomial order equal to 3, so we're raising it, and the interval AB now becomes the interval AB by the second knot and the fourth knot. Okay, actually, we are counting from 0, so it's the third knot and 5th knot. Okay. So let's go on. 4 basis functions in this case. Okay, we raise the order, keep the same knot vector. The number of basis functions decreases of 1. As you can see, this is the expression. I'm not going to read it. Believe it or not, you can try your computation on your own. But actually, this is the way you express the weights and the linear combination with the previous order B-splines. Okay? Let us see some examples. Now, the shape of the basis functions, as you can see, is polynomial. We are polynomial degree equal 2, since the order is k equal 3. And as you can see, again, we have some bump-like functions. We have, as you can see, 0. Otherwise, the support. So somehow we have some compact support properties. We will see better later. And moving further, the second one, and the third one, these still keep the same shape, okay? Okay, then, this is the overview for polynomial degree equal to 2, and of the basis functions, of the 4 basis functions we have introduced. Very nice. So, what happens? Okay, this is a lot of the other examples. What happens if we play a little bit different with the knot vector, okay? We are allowed to introduce the multiplicity of the knots. We are allowed to change the knots that come previous the extremals and after the second extreme of the interval of the domain. So the very first picture shows you an example where we have used the polynomial degree equal to, okay, the same basis function, maybe some more knots, and plus, I don't know if you can read it, but I reported all the knots in a second here. We have repeated the first knot 0 3 times in this case. So we are using order k equals 2. We repeat the very first knot 3 times. What we have is that the interval AB, where we are defining the basis, now becomes starting from 0. Okay? And as you can see, the very first basis functions has somehow been collapsed in the left part of the graph and goes up until 1, okay? Another property that we will discuss sooner is that, as you can see from all the pictures I've shown you, these basis functions never overcome the 1 value, okay? We'll see later why. Okay, of course, by the definition. But let me just say, what happens if I do the same stuff on the right part of my domain? So I repeat the knot 5 3 times, because the order of the polynomial is 3. This is called, this structure is called the open knot vector, okay? And the polynomials at the very first one basis function and the last one, as I said before, they collapse, but they mean that at the extremal of the interval, they reach the value 1. So these knot vectors are called boundary interpolatory somehow, okay? Because if you want to approximate, let us want to approximate a function with some polynomial basis, and we use this one, define it this way. At the extremal of the interval, we will interpolate the data, okay, or the function. Very nice. The picture on the right is just for order k equal 4, okay? I use the degree 3 splines, so cubic polynomials, and the same knot vector. But I had to repeat the first and last one the same 4 times. The order is 4. Okay? So nothing changes as before. We have added 1 basis functions. Okay? And we have repeated 2 knots. Okay, really a strong connection between the knots and the basis functions and their shape. And in the bottom of the screen, you can see this picture here. Not only I've repeated the very first one and last one knots, but I have used some repetition of this knot. I can see which one is. So it's too small, but I've repeated 3 times this knot, and the shape of the basis functions has collapsed also in this point, and this green one, has gone up to 1. So somehow I'm expecting, again, in approximating functions, that at this point I will be interpolating the data or the approximation I have. Okay? Plus, I've selected also an extra knot. I inserted also an extra knot here, and somehow I've produced a non-uniform partition of the interval AB. Now in this case it's 0, 6. I can't read it, sorry. And don't remember it, of course. But as you can see, the polynomial basis functions, somehow we have inserted another one here, because we inserted one knot, and somehow they are collapsed all together because there are very few space between this knot here and the very end of the domain. Okay, this was just to show you some particularities of how you can create this polynomial basis, how you can play with the knots, and how the basis reacts to the movement, to the change that you make. And let us talk about Bernstein basis. Some of you know about Bernstein polynomials. Okay? I can see some faces, but some other others just tell me, no, I don't know. Okay. What are Bernstein polynomials? They have been used a lot in the past for design, starting from also before for the designers that implemented the shapes with hand, with the splines. If you remember, spline is an old tool, let's call it like that, in wood, and designers changed that curve. It's really a curve in wood or plastic. I don't know why, but that can be changed a lot. They use it to design the shapes of, for example, in automotive industries, of cars and I'm not an engineer, never tried it, but they used these kind of basis functions, Bernstein polynomials. Okay, and they are simply, in the context of these splines, they are simply a particular case. Because if some of you know how they are defined, okay, fine. Otherwise, we can get them just selecting some particular knots, not vectors. Okay. First of all, for degree 1, so order k equal 2, we just have the knot that has the very first extreme of the interval and the second extreme, and we repeat it 2 times. Okay, so the knot vector is given by 0, 0, 1, 1 in this case. What happens? Okay, this is the shape. If I want to raise the polynomial degree, let us use p equal 2, so order k equal 2. I will expect to repeat 3 times the 2 extreme of the interval where I'm defining the polynomials. That's it, and that's what happens, and we get the Bernstein polynomials. Okay, same game. Let's call it for the degree 4 and degree 3 and degree 4 polynomials. Okay, so we can recover these Bernstein basis functions starting from this line. So we are somehow introducing let us say a general recipe for all these polynomial shapes. Okay. I just want to talk with you about some kind of other properties, but very in a quick way. So let us fix, as we did before, polynomial degree. So the order k is p plus 1, knot vector, and so on. The basis functions, okay, I already told you, but very simply, they have a local support. Okay. It means that, by definition, of course, you can prove that the basis functions are 0 outside a particular place in the support in your domain. Okay, sorry, in your domain. And usually the basis function, the if basis function of order k, is not zero, so it's not zero, it's different from zero, just in the interval ti plus k. Okay, k is the only in this interval we have the support of our basis, and they told us the basis function, they are non-negative. Of course, with the pictures, you've already seen it. We have some polynomials that are always greater equal than zero. They are zero just outside the support, and we can write explicitly every time the support, which is. We just need to know the null vector and the order. Okay? And of course, the basis functions we are selected. Plus, a nice property, and that's why I told you they can overcome one, because they form the basis functions we introduced. The B-splines form a partition of unity. That means in the domain of definition of your basis functions, so in this case, AB will be this not T2 up to T4. So it's the previous case, order, if I don't get it wrong, order 3 polynomials with a not vector that was 0, 1 up to 6, okay? If you remember. As you can see, I've selected for you the support of these basis functions, so you can check that it's exactly given by this one. Okay? They are positive, of course they are over 0, okay? And the partition of unity means that if you sum in a fixed point of your domain, if you sum all the basis functions evaluated at the fixed point, T star, okay, you will get 1. That's simple. Okay? In fact, the black curve, that's the point of the basis functions, is simply the computation of all the basis functions evaluated at a fixed point in the domain and summed all together. And as you can see, in A, B, they go up to 1. Okay? Then I think that I will stop here. I've just introduced you what are B-splines, how you define them in the simplest way, easiest for computation, from the computational point of view. We will see later what are B-spline curves, okay, and how to use this B-spline basis that we have introduced. Okay? I suggest you to have a coffee break. I guess it is already prepared at the table. So thank you for your patience. Have you? Okay.
Is there any question on this first part of the talk?
Okay.
Please.
Can you take the definition of the not vector? Maybe I lost it. But let's say the step has to be constant, or can you take
the step between each knot?
Yes, let's say tk minus 1.
Okay.
It has to be the same for every k, or?
Okay, sorry, this. Okay, I can see now a mistake. It's my fault. There's that tk minus 2 missing. I repeated tk minus 1. But no, it must not. As I told you before, I put just one example of non-uniform partition. Okay, you have to imagine that the not vector forms a partition of the interval where you are, okay, starting from t0, interval defined by t0, tn plus k. Okay, it forms a partition of the interval, and you can take, since you have lower equal sign, you can take also a repeated not. Okay, we have seen it.
Okay.
And plus, you can take a non-equal distance between the knots. Okay.
Sorry for the question, but what's the difference between spline and B-spline?
Okay, what's the difference? Because,
Not that I know what splines
no,
are.
spline is
It's
just
the
general term. Okay, these are called B-splines because B stands for basis, or what I remember among the courses that I followed. No, this is just simple a way to introduce a basis of already spline functions. Okay, they are smoothly because they depend on the regularity because of course if you repeat one one thing that I did not tell you. If you repeat the knots, somehow you have to pay a price. So if you want to be interpolatory, fixed point, somehow you have to, so you are approximating very well the data, but you have to pay a price for this, okay? And the price you pay is that you lose some smoothness, okay? Let us call, if you don't have internal repeated knot, the smoothness of the basis is CP, okay? It depends on the polynomial degree, okay? But if you repeat some knots, you can see it from the itself from the image, from the picture I showed you. Okay, you are not continuous here. Okay, you are continuous here, but you are not neither C1. Okay, so the derivative goes up to one stop.
Right, so I just got a question because you mentioned the Florence polynomials.
Yes.
So those are the same that are used in the proof of Bayes approximation theorem, right?
Okay, yes.
And that's
yes.
one variant.
Yes. That's a fun fact. B-splines have been introduced exactly for the proof of the.
Oh, right.
Okay, the versatile ones, so no B-splines, have been introduced for the proof of Wasserstein theorem. Okay. Wasserstein approximation theorem, not Wasserstein theorem. Okay. They have been versatile polynomials have been introduced for that fact. Never used, because if I don't get it wrong, it's about the early 19th century, 20th century, sorry, early 20th century. Okay. I don't want to be wrong in this part, so let's say that they have never been used up to 1940, 1950, when engineers and designers from the very first one, maybe from Renault automotive, and if I don't get it wrong, maybe Peugeot, maybe Citroën, sorry, thank you. Okay, fun fact, they use it in design, and they have seen that with the calculators, then they had some nice algorithm.
Thank you.
Okay, any other question? Okay, let's start. Okay, let us continue with Sofia, and she will now start to talk about the B-spline curves.
Thank you very much. So B-spline curves are often used in a computer-aided design environment. So we start setting the polynomial degree P and the order, which is P plus 1, and we fix a knot vector or an extended knot vector on an interval of R. And I want to stress that when all these ingredients are set, our spline space is defined. So, and on this space, we are going to give this definition. So that's a B-spline curve definition, where for each basis function, we associate to it a control point, which is called Ci. So B, I, K are the basis functions, C0, C, N are the control points, and they are in R, D. D is the dimension, so usually for application is either 2 or 3. And then that's what we get. That's by this definition, that's an example of a B-spline curve. And the line which connects each control point to the following one is the so-called control polygon, or in a surface environment in higher dimension, we also have a control net. So let's see some properties of these curves, which are used, as I said, in CAD environments because they are extremely flexible. All the B-spline properties, all the B-spline curve properties comes from the B-spline properties, which Alan mentioned before. So locality, local support, non-negativity, and partition of unity. So from the local support of the B-splines, we have a local influence or a local effect of the control points on the curve. That is that one control point influences the shape of the B-spline curve only if you are close enough to it, let's say. So here you can see in this image, so if we change this control point a little bit, we can see that this curve, those two curves are a little bit different, but only if we are close enough to this change. Far away, the B-spline curve doesn't feel this motion of this control point, for example. So this is very useful because we can play with the control points as a kind of a marionette or a puppet. Moving the control points, we are able to control the B-spline curve. Then we have the so-called strong convex hull property. That is that we know that the curve lays on the convex hull of k consecutive control points, where k is the order we set, so degree plus 1, polynomial degree plus 1. So here it's trivial case where the order is 2, so actually the curve coincides with the control polygon. So I don't know if this image you can really see it, but maybe that's a better one. So we set k equals to 3, and we can see that the curve lays in the convex hull of k consecutive control points. So in this case it's 3. And this, it's always true. So again, by knowing the control points, we already know where our curve will be. And this is also for design a very strong tool to use. Another example for k equals 4 is the same. So this is the convex hull of 4 consecutive control points. If we play with the space we are dealing with, we can also modify a little bit the shape, of course, of our B-spline curve. And as Alen mentioned before, we have also the interpolation. In particular, if we repeat the k-1 left knots and the k-1 right knots in our extended knot vector, we have the endpoint interpolation of the curve. That is that the B-spline curve interpolates the first and the last control points. So we can force the B-spline curve to pass through specific points. So again, this picture, maybe you cannot really see it, but that's here the curve doesn't interpolate, it ends here, because in this case the knot vectors at the beginning and at the end are not, the knots in the knot vector are not repeated, while here we have interpolation. Furthermore, if we set certain spacing between the knots in the knot vector, that is, we use so-called cyclic knots, so the space between the first k-1 knots is the same as the last one, we can also construct closed curves, B-spline curve. If we set the space, so we don't touch the space anymore, we can still have very different configuration of our B-spline curve thanks to the control point themselves. So for example, here, if we take k-1 aligned control points, we have that the curve will touch the control polygon in a certain, on the line which connects this k-1 control point. So this is an example. So we have 3 control points aligned, and we have that our B-spline curve touch the control polygon on this part. Furthermore, if we have K aligned control point, we have that B-spline curve coincides with a part of our control polygon. And in the end, if we take K-1 coincident control point, we have that the B-spline curve interpolates the control polygon in this repeated control point. So again, I would like to stress that those configurations, this 3 last configuration we have seen, they are we achieve them only playing with the control point and not with the space. Furthermore, we have some other properties which could be also very useful, in particular in computer graphics. That is the variation diminishing, which means that if we take a B-spline curve and its control polygon and a line, the intersection between the B-spline curve and the line will be less or equal than the intersection between the B-spline curve, between the control polygon and the same line. So here we have 1, 2, 3, and we have the same for the control polygon. But here, for example, we have 2 intersections between the line and the control polygon and 0 with the curve. And in the end, if we want to perform an affine invariance transformation on the curve, we can just perform this affine invariance transformation on its control points, and that's all. That's the only thing we have to take into consideration. As regards, thanks to the definition of B-splines, we are also able to get an expression of their derivatives. That's, as I said, just thanks to the definition. If we know the B-spline, we can just derive them and get a clear expression of the derivative of the basis. And we just have to replace this definition inside our curve, the expression of our B-spline curve, to get also the expression of the derivatives of the B-spline curve. So everything, it's already there. It's like cos 0, and we have also the derivatives, order 1 or even higher, just by replacing the expression of the basis. Furthermore, I will introduce you 2 other fundamental geometric algorithms, which are the Debar Algorithm, the first one, which is useful in order to evaluate a B-spline curve. In numerical analysis, the evaluation of the function is usually a very expensive step, but here it won't be, because in order to, thanks to this algorithm, and just by replacing again the definition of the B-spline basis, we can get the value of a curve on a certain point, just knowing its control points again. So we perform a so-called corner cutting strategy or constructions, and we just compute the value of the B-spline curve in a point, knowing the combination of its control points. So this is also less expensive as in other settings. And another important algorithm is the knot insertion. So what's knot insertion? We have, let's suppose that we have a knot vector, and we want to add a knot. That's what we are doing. So we are actually considering a bigger space, because an additional, if you remember, there is a strict correlation or relationship between the number of knots and the number of basis function, fixed the degree. It was at the very beginning. So if we add another knot, actually we are adding another basis function, so we are consider a wider space. And the fact is the introduction of these knots will affect only certain basis function of the previous basis, and we can still compute the expression of a B-spline curve in the new basis, with the new basis, again starting from the definition and from the previous basis function and the previous control points we had. So we have, again, I'm not going to read all of them, but we again have, let's say, a closed expression. So we can really, as soon as we insert a knot, we already know how the control points of our B-spline curve will change. And again, not all of them. Some will stay the same, some other will change, thanks to locality. So this is an example. Actually, here we add more than one knot. We add 4 knots by just splitting the previous knot spans. And here we can see that we have exactly the same curve shape. So we are able to represent the same curve, but with a little bit of different control points. Of course, every time we insert a knot, we have to change locally the control points referring to this new knot. Because for a new knot, we have to introduce a new control point. Briefly, I would mention also the NURBS, which are the non-uniform rational B-splines, because B-splines are very nice, in particular in a design setting, and as I said, I hope I convinced you that the B-splines curves are really flexible and very useful, but they cannot really represent all the shape we want. For example, we have some troubles with exact circles or elliptics or similar shapes. So these NURBS were introduced in order also to deal with this shape, which the B-splines cannot represent exactly. Of course, we can approximate, but sometimes not enough. So this is just the expression of a B-spline of a NURBS curve, and here we have the B-spline basis function. Here we have the control points, and here we have this beta, which are the sum weights. So it's a weighted sum. We can also give an interpretation, a geometric interpretation of this definition. So we can consider a B-spline curve in R3. So we have 3 components, and we define in a proper way its control points, these coefficients. So we can say that the NURBS curve is a projection of our B-spline curve in R3 to R2. So here maybe there is an example just to clarify this interpretation. So in R3, here we have a B-spline curve. It's a B-spline curve. And as soon as we get the projection, we have a NURBS curve. And thanks to NURBS, as I mentioned, we can draw circles or also some ellipses and other shapes. So now I would shift to this so-called approximation problem, which in the general setting is the following one. So we are given a set of points in RD. As I said, in application, usually it's either R2 or R3. And we want to find a B-spline curve which approximate them. So for which the approximation error is as small as possible. we can define our approximation error as we prefer with some distances. For instance, that's just norm to distance. So we have the points, pi, and a certain curve that we will evaluate in a certain parameter corresponding to this point, ui, and we want to minimize this error. Of course, there is another problem related or linked to the approximation problem, which is the parametrization problem. As I said, we have those points in the space, and we have a B-spline curve. But there is no functional relationship between the B-spline curve in the space and on the R line. So we have to evaluate the B-spline curve on proper points on our interval in order to have a fair comparison between the B-spline curve and the points. So we have to find also those parameters. So each parameter, ui, will correspond to a point in the space, pi. There are some standard so-called a priori parametrization. So we are just given, suppose we are given a set of points. We have the uniform parametrization of these points, so just I over the amount of points, or the so-called centripetal or Chon-Length parametrization. So that's, for example, that's a uniform, that's a B-spline which approximates those points. We have set, let's say, an order and a knot vector. We build our curve, and we evaluate this curve on these parameters, which are computed with the uniform parametrization. And that's like the B-spline curve, which approximate with this parametrization in the best way these points in R2. That's another curve, which is in the same space. So we didn't change the spline space. We just changed the parametrization of these points. So considering a centripetal parametrization, whose expression is here, and which try to imitate in the parametric space the spacing and the relationship between the points in the space, in the real space. So just changing the parametrization, we find another curve, which is the best approximation for these points in the same space. And again, changing again in the same space the parametrization, we find a third different curve. So the question is, of course, which is the best parametrization? I mean, the best one is the one which reduces as much as possible the error, but how to find it? Because there are several. Those are just, as I said, a priori. So we first fix the parametrization and then we compute the approximation. But there are thousands of other parametrization which are done like in an iterative way. So first we make a parametrization, that's an approximation, then we go back and we change the parametrization again. But they are also kind of expensive. Those are the standard ones because, as you see, they are just one line code and they cost almost zero. While with the other and this optimization process, of course, the cost increase a lot. So my approach is to try to involve some neural networks. So I don't know how much you are familiar with neural networks and deep learning, but let's say that deep learning is finding its space between artificial intelligence and machine learning. And the key point, I mean, why I'm using neural networks, because I want the machine or the computer to find by itself the parametrization. I use deep neural networks which lays in deep learning framework. And let's say, in a naive way, we can say that the difference between the machine learning and the deep learning is that here, in a machine learning setting, the user is required to give the machine also some features. I mean, to pass the data and also to tell the machine what is important of this data. For instance, in our point clouds, we could say that a feature could be the relative distance between the points, for example. But those are all information that the user is deciding by itself, or himself, herself. While in a deep learning setting, we don't declare these features. So the machine has also to understand which are the important features, to extract them and to use them. Briefly, a learning problem is defined by defining a space X of inputs and Y of output, and a probability distribution over X times Y. Our data, so that's just like in theory, but then we work with data. So that's another important assumption, that is that our data are independently sampled from this distribution, which is not known. That's the difficult part in the machine learning or deep learning setting. So we don't know this distribution, otherwise it will be already done. What we want to find is a functional relationship between the input and the output, which represents somehow or approximate the outputs. So we want f of x to be as close as possible to y. To measure the wellness, or how this functional approximation is good, we use a so-called loss function, which is the cost of predicting f of x instead of y. And a learning problem is actually a minimization problem. A minimization problem of the so-called expected risk. So this is the formal definition. However, as I said, we don't have P. We don't have the probability distribution. So we cannot minimize the real expected risk, but we have to minimize a so-called empirical risk, which is an approximation of the expected risk. So in deep learning, this functional relationship between the input and the output is computed using deep neural networks, which are some kind of networks where we have an input layer, where are the data from X, several hidden layers, and then a so-called output layer. So here, let's say that the magic happens, and we find our functional relationship between input and output. Deep neural networks, another difference between the machine learning setting, for example, is that we don't assume linearity between input and output. So in machine learning, there is not only regression, we don't only have a line, linearity is not always so outstanding, but there are some kernels and some other tricks which assume that there is a kind of linear relationship between input and output. Here, the linearity is broken. And as I said, we don't declare which are the features of our data, but the machine has to learn it by itself. And we have, in order to deal with neural network, to train our network. And to train our network means actually to set and to identify these weights, because here we have all connections between the input and all the other neurons. All these errors are actually weights, and we have to find these weights, because at the beginning it's just empty. It's initialized as 0 or randomly, as you prefer. So the information goes from input to the output, and in order to follow this path in a forward manner, we need some kind of activation functions. I don't want to go into details, but I want to just to give you the feeling of how many the so-called also hyperparameters we have to decide. Because also activation functions are something the user decides when it's setting its neural network, as well as the loss function. So there are different loss functions in order to measure the error. One has to choose the preferred one and go on. In particular, I'm using some convolutional neural networks where the layers, the convolutional layers, are based on the convolution operator. So here we just have an example. So here is the matrix of input. We have the input, and we have a so-called kernel or filter. And the fact is that we overlap this filter on this matrix, and we do the convolution operation, and we get the output. So and then we just shift a little bit, and we do the same for all the input. On the same input, then we can also place several filters and have also a kind of multiple layer output. So again, I'm not going into details, but I want to again try to make you understand how sensitive and how different all these networks can be one from each other, because all these settings are something which the user decides. So I decide how many kernels to put on the inputs and so on. Why I decide to go to convolutional neural networks? First of all, because we have, thanks to these convolution operators, as you can see here, it's not really a matrix multiplication, and we can manipulate as we prefer also the dimension, and we have also a lower computational cost. Because if you remember this slide with the, let's say, the very first neural network I showed, the fake one, there were a lot of connections between all the neurons in there. But here, those connections are way less. So we save some cost. We have a kind of equivariant representation, but most important for my research of interest, which is this point cloud approximation, thanks to B-spline curve, is that we can deal with input of variable size in theory. So that is, I can, usually the input has to be of a fixed size. I work with 10 points, 15 points, 100, but it has to be the same. While here, I could vary this amount of points. In this case, when we train a convolutional neural networks, it means that we are setting the filters, so the filter numbers or values. This is a little bit the setting that I decide for my convolutional neural network. In particular, I choose this activation function. I choose the mean square B-spline curve approximation error as a loss function, and I choose a 1D convolution because I just put my points, let's say, only in a column. So no matrix, no 2D convolutions, but one. But the principle is the same. So the filter just go through all the input. And this is a little bit the setting of my neural network. So I have the input, I have 4 convolutional layers, and here I just stated one fully connected layers, but actually I tried different neural networks. Sometimes I used only one, sometimes I used a little bit more. And I have still to understand why you need sometimes more and why you need less. That's but so we take the input, the process start during the training. When we are actually in the output phase, we compute the loss function, and yeah, if it's enough, if it's enough low, it means that we are the training is good. Otherwise, all these parameters will be set in a different way. As you see, the output of the loss goes again with the input. So it's given to the neural network together with the input. And thanks to this value, to the loss value, the neural network understands how to balance its weights. And this is just an insight of these convolutional layers. So I have 1D convolution, a batch normalization, and the activation function, which I showed you before. This is called realm. Yeah, this activation function. And those are some of the results. So first of all, another important things I have to stress is that for training a neural network, you need data. And to find this data, you need usually a very huge amount of data, and it's not so easy. So around just to find thousands of point sequences in R3, for me it was not easy to grasp. So I have to make my own points. So those are only artificial points. And in particular, I just generate them sampling for B-spline curve of degree 3, polynomial degree 3, order 4, with a random knot vector, with a number of knots between 0 and 20. That's because of my choice. I could have gone between 0 and 5, 0 and 30, just up to me. And with also a number, the placement, the knots, the interior knots of the knot vector are also randomly placed. So they are not empty space, they are not uniform, but I just place them randomly, of course, in an increasing way. So orderly, but still random in placement. So I generate here 241,000 B-spline curves, and from each of them I sample a sequence of 10 points. Then I split my data in training, test, and validation set. And so I train my network on the training data, and then the validation set is useful in order to understand how your how your training is going. Because in the meantime that the network is training, you also, let's say, test it. It's a little bit tricky to use this verb again, but you say, okay, I train, I went through the network only once, that is one epoch. How are my weights? Are they already good enough? To understand this, I test the network with these weights on the validation set. If the error I get on the validation set is low, it means that, okay, my training is actually going well, and I can even stop it. So that's not part of the loss function. Okay, so the loss function tests the error still on the training data. And the network decides its sets basing only on the training data. Here, the validation set is useful for the user to understand when to stop to train the network. Okay? Because if you are still training, but your error is increasing on data that the network has never seen yet, it means that something is going wrong, for example. And at the end, I have the test set. And those are the results on my test set, on this test set. So here I have I approximate this data with on the same spline space always for all these four parametrization of the points. The degree is again 3. And here I have, for example, the B-spline curve approximation error with the convolutional neural network parametrization. And I have Hausdorff distance, the mean square error, and the maximum error. And we can see that the approximation error is always lower. So we are approximating better those points while using the parametrization given by the CNN instead of the standard ones. The same, and here, as I said, as it's written, as I said, the space is set, and I'm using the so-called Bezier curve, which Alen introduced you before. So with no interior knots. That is, I only have the knot vector here is 0, 0, 0, 0, 1, 1, 1, 1. No interior knots. And those are the results. Here, I have other data. I mean, they are more or less the same, but I generate them again, just always fake data more or less, so data I make. And here I approximate those data points of my test set with a B-spline curve this time, with 3 interior knots. Now, also the knot placement, it's a very delicate issue, but let's say that here I use for each parametrization also the corresponding best knot vector. So the space, it's a little bit different for this parametrization, but it's the best one we can find for each of them. So I would argue that it's still a fair comparison, because I am calculating, for example, here the approximation with the centripetal parametrization with the best knot vector, so the best space I can find for this parametrization. And again, here, for example, I needed 5 fully connected layers, so the problem is getting a little bit more difficult. The space is wider. We have more knots, more basis functions, B-splines, not Bezier. And with only one, I mean, I have to say that the results were on the same level. So it was still good results. I mean, it's not that my CNN was giving me high errors, but still not worth it. Because as I said, the centripetal, the channel, and the uniform are all one-line code. While training a neural network, it's way more expensive. So if I use a neural network, it has to be worth it, of course. If I get the same error, it's not worth it. I can use a standard parametrization. But here, again, thanks to the Hausdorff distance and the mean square error and the maximum error, we can see that we, again, improve our approximation error. And that's all about B-spline curve and my research topic so far in this first year of my PhD. And yeah, then.
Is there any questions for Sofia?
So if you go back to the first slide, right? No, sorry, not the first slide. Not this one, the one. No. Okay, this one. So you see that the MSC has been gained more or less one order of convergence with respect to any other one, while you don't gain any order of convergence in the other comparison. And is this due to the fact that you use, at the end of the day, MSC as a loss function? What happens if you use the DHD or something similar as a loss function?
I don't think so, because either Hausdorff distance and maximum error are the maximum error, so the biggest error you get, so the biggest distance between the curve and the sequence of points. So here maybe it's given between the Hausdorff distance or the maximum error are registered for the point number 3 of the sequence, maybe here for point number 1, maybe here for point number 8, and so on. So the mean square error, it's lower. It means that in general, if you just make a mean, you get a lower error in general for each point. So maybe there is a big one or a bigger one, but in general, the error is smaller. So yeah, I think it's just by the definition of this Hausdorff distance and maximum error. And I think you don't gain a lot, and that it's kind of fair also because we are approximating this point. We are not interpolating. And we also have to consider, for example, some kind of noise, maybe, or, I mean, we don't have the ground truth. We don't know actually if going so close to the points, it's very good. Maybe because we don't have the ground truth, the curve these points we are sampling from. I mean, we could, because those are data I generate, but in general, for real application, you usually don't have. So, yeah.
So do your points have some kind of order when you fit them? So I mean, perhaps you can get one curve, the one that you showed before looked like a hook, right? Maybe they can go the other way around. So are the curves the same? Is there a way to guarantee this?
Yeah, I didn't mention it. That's true. Because so the space I generate my points is the same for each curve. And so I play only with the control points. If you remember, playing with the control points give you the possibility to play and to change the shape of the curve. So no, there shouldn't be any guarantee because also the control points are random, so are generated randomly according to a normal distribution. The only thing I wanted to change a little bit is that this normal distribution change for each control point of the same curve. In particular, I changed a little bit the mean of this normal distribution in order to have them a little bit more spaced. But just because if you don't do it, you get really a lot of self-intersecting curves. And for real application, it's not good. I mean, it's not, the network still, I trained the network also on this kind of data with this full of self-intersections curves. But then when you go to real world and real applications, nobody wants a curve which intersects itself several times. It's not good, it's just kind of mess. So I try to avoid these self-intersections, a little bit spacing. There are some, because I wanted to have some of them in order to be as much general as possible in this setting. So there is this chance of self-intersections, but I try to space them a little bit more. But so the answer is no. There is no guarantee about the points placement.
Yes, Francesca. If I remember correctly, if you have control points which are repeated, you can get an effect which is not identical but similar to the effect you have when you repeat nodes in your mathematics, right?
Mm-hmm.
Here you are using 10 points chosen at random. Right?
Yes.
And the probability that you are choosing repeated nodes points is quite low, right? What happens if in your in the points you are choosing for your test there are repeated points? If you are not considering, or you are considering very low probability.
Yeah, so having a look at a training set, validation set, and test set, yeah, this probability is very low. I would say almost zero. I've never seen some repeated control points. Also because it has to be repeated k times. So, I mean, it can happen twice, but if they are repeated twice, you cannot really see anything on the curve, but they have to be repeated k times, so maybe it's a very low probability that by chance it will just happen. But I don't know. What I expect is that if I train on this set, so with a training set with where this phenomenon happens a lot of times, I expect my network to learn it, and when it will meet some other points of the same nature, it will be able to reproduce them. But it's very good to also to be as much general as possible in the training set. Otherwise, when you go on the test set, the network has learned just this configuration, and so it won't be able to deal with new configurations.
And if you don't train your machinery to learn what happens when you are repeating nodes. What happens if you by chance decide to have just one sequence of points in your test set with repeated nodes? It will mess everything up.
If it has never seen them, probably yes.
Can you go back to the minimization when you describe the learning problem as the minimization problem? Okay, so you said that your probability distribution is somehow unknown, right?
Yeah.
But let's say right now you're building a specific network for a specific type of problem in which you know that, for example, a region of the points will have a greater importance in the well approximator rather than others. For example, it's a high stress region, and therefore you want to do approximation that then you will use in IGA, and you know that in there you need better approximation property for IGA. So you want there to be a better approximation. Can you play with the probability distribution? Can you somehow, when you go into the empirical risk, take this into account and mimic some way a behavior of probability distribution that you would like?
Yeah, you need good data for that. You really never know the probability distribution. So you can, as a user, try to guess it or to tell the network, hey, try to behave in this way, showing a network points, I mean, not points, in this case, data, any kind, I mean, I've been speaking about points, but we can give the network everything we want. So other data, but you need data which fits your problem.
The assumption that you're doing is that somehow the probability is unique from there, right? When you pass to the empirical risk, you're assuming that everything is worth one. Sorry, everything is worth the same, right?
Yes.
So, but can you somehow get a higher probability to some points that satisfy certain property rather than other and still train your network in the same way?
I mean, I'm sorry, but my answer would be kind of the same, because, I mean, everything is worth it the same, but if the network sees several times the same kind of data, thanks to the loss, which is the loss, I mean, the loss you decide, so maybe that's also the point. You have to choose the loss and to say, that's the error you are making, but the loss has to be appropriate to the problem, for example. In classification,
include this into the loss function.
Yeah. So not on this, no, I'm sorry. This is unknown and you don't know it. You will not know, never know it.
Okay, if there's no other question, let's thank Pavia again and see you in 10 minutes from now.
Yeah, 10 minutes,
Thank
if
you.
it's okay.
We can make also a bigger rest.
Okay.
20 minutes maybe if you want to rest because it's 2 hours. At least Zebinato was asking me if we could have a sort of long break at the okay? Not to have 2 hours, 2 hours. If it is fine for you.
20 minutes then.
Okay.
Okay.
Thank you.
So welcome back from this long break. So now Alen continues with isogeometric analysis. Please.
Thank you very much. Okay then. In this part, I would like to introduce you to isogeometric analysis, the main idea, and the main. Sorry, you told me not to work so much. No, I'm just kidding. I wanted to introduce you to isogeometric analysis, to the concept itself, to why it has become so flourish research area, and of course how it works, some basic techniques, and in the very latest part, I will show you some of the topics of my research field, okay? Of my research. So let us start with this nice picture here. Okay, this wants to resume an engineering process. Okay, Sandia National Laboratory published this nice picture, and Tom Hughes, one of the pioneers that introduced isogeometric analysis in 2005. 2000. Sorry for my English mistake. Okay, introduced this concept very recently, and wants to point out that when you want to make some simulations, you have your problem, your partial differential equations that govern it. You want to somehow solve it, but maybe it's large, maybe it's difficult. You want to do it numerically. Most of the times, at least in history, people use finite elements. Nowadays, still using finite elements. And I don't know how much you are familiar with them. I don't want to cover that topic. But this is somehow the recap of the process. You have your domain. You have to approximate your physical domain in your machines. So you are constructing the approximations of the domain, and plus you need a mesh. A mesh that is simply this partition of your domain in many triangles or squares, or many methods can be used. And all this process of approximating the domain, creating a mesh, requires a lot of time, really a lot of time. Then when all the stuffs are set up for your simulations, you adopt your numerical method, you perform your simulations, and you're done. You have your solution. But maybe, okay, your solution reveals some mistakes or some bad approximations, okay? And you have to come back and start again. You have to change a little bit the domain, maybe. You want to perform another simulation on that. This process of approximating the domain and meshing, it's called exactly meshing, it requires about 70% of the time, okay, for all this cycle. It's quite enough, and it's a handmade work, okay? And you can spend also 1 month just meshing, for example, one tire. It's crazy, okay? And you are not alone, you're involved in a team of experts. And the idea of Tom Hughes is, how can we simplify or optimize this process? And isogeometric analysis would like to make to build another part of proceeding without requiring these meshing steps. Okay? So, okay, in this picture, I just wanted to show you an example of this is a part of an engine. I don't know exactly, but these constructions are made with CAD softwares. Okay, and maybe Sofia mentioned it before. CAD softwares reproduce shapes and geometries using B-splines or nerves. Okay, So, all this beautiful image, it's simply parameterized by splines, the same ones that we have introduced before. How can we, now imagine you have your splines that parameterize your geometry. Now you want to apply finite element and you have to approximate this geometry. That sounds crazy, okay? It sounds a waste of time. Okay? And the basic idea is to use this geometry already given and continue with that, your analysis and your discretizations. So first of all, as you have seen, that was a shape in 3 dimensions. So we have talked about curves, okay, in RD dimensions, exactly. How to construct surfaces or shapes like that. Actually, the very basic idea is to use tensor-product construction. Okay, so we have introduced B-splines in a univariate dimension. Okay, and just to remember it. Okay, I don't know if you can see it, but I put an hat on top of the B, I, K. Okay, just because we will deal with a parametric domain and a physical one. Okay, and on the parametric domain, the B-splines are defined at least univariately on the interval 0, 1. Okay, so the hat wants just to remind you that we are in the parametric context. And so the B-splines are defined over there. And I want to call SP, T is the knot vector, P is the polynomial degree, the span of these basis functions over 0, 1. Okay? How to build a B-spline space over, for example, 2-dimensional multivariate case, in the multivariate case. The idea, I told you, is to use tensor-product. So usually D, the dimension will generally be 2 or 3 for at least most of the numerical experiments. So you have to introduce now a degree vector P, bold P, that has P1 up to PD degrees, 1 for each univariate direction you are introducing in the space, in the 3-dimensional space. Okay. Or in RD. Of course, the order vector will be K equal P plus 1 a vector of all entries 1. And I also wanted to use this notation, bold theta, bold capital theta, for a set of all the univariate not vectors, okay, that are T1 up to TD. Okay, nice. TL, one of them would be just T1, TNL plus PL plus 1. Okay? Starting counting from 0, not from 1. Just to remember this one. Okay, now we can construct some multi-indexes. Okay, I just introduce these J multi-indexes. JL goes from 0 to NL. Okay. For each univariate direction, they will count the univariate B-spline basis we have. Okay? And the idea of tensor product is simple. You make the tensor product of the univariate B-spline basis you have. And the tensor product, in this case, reduces to exactly to the product of the basis functions for each univariate direction. So you introduce the multivariate B-splines as the product of the univariate ones. So it will be evaluated in a certain point of your RD domain, okay? And for each univariate entry, you will evaluate the univariate B-spline and then make the product of them. And we call by bold S hat P and theta the span of these basis functions you get. Okay? Here's an example of their shape. Okay? In the univariate case, I mean, in the first univariate direction, you will have a polynomial shape, and the second univariate direction, you will have another polynomial shape. We make the tensor product, and we build these bump-like functions, okay, all around the domain. this is an example of, I guess this was order 3, okay, degree 2 polynomials for each univariate direction. Okay, very simple, and with not repeated internal nodes in this case. But as you can see, we are interpolating. So the previous one is interpolating, so we are using open node vectors. And just to remember. Okay then, finite element has a mesh. We don't have a mesh here because we didn't introduce any triangularization of the domain or something like that. We can construct a parametric, it's called parametric Bezier mesh, simply by this procedure. Okay, this ZL want to count just the unique values of the knots you have in the knot vector from one direction, from one fixed direction, L. And you use this in order to build some intervals, okay? Zeta direction L, J, I, J, okay, what I'm using? Okay, JL, JL plus 1, okay? So just two unique knots that are close to each other. And the mesh itself, it's made of these elements, Q, J is the multi-index introduced before, and it's exactly the Cartesian product of all these intervals in the univariate directions. Okay? This will form a mesh in which a domain, in the parametric domain, 0, 1 to the d. Okay? And the parametric Bezier element, okay, it also has a support extension. I never told you about support extension. In the univariate case, imagine the support of your B-spline. Okay, take a not span ti plus 1. The support extension of not span in the univariate case is simply the union of all the supports of the B-splines that are active on that not span. Okay, it means that are different from 0, so greater than 0 in that not span. By the way, it's an extension, and it is known as soon as you know the degree, and it's given by this interval here. And if you make the Cartesian product of those intervals, you get the support extension in, for example, in 2D, 3D of your elements in the Bezier mesh. Okay, so your mesh is just like this, and you didn't have to triangulate because you already know all the knots in the univariate directions. Okay? So no difficulties on building a mesh on the square, for example, in 2D. And if this is an element, okay, this is the support extension. In this case, in the first univariate direction, we are using, since the support is 3 not elements, we are using, for example, degree 2 polynomials. In this case, we are using degree 1 polynomials, order 2. In this other univariate direction, we are using degree 2. Okay? We can choose the degree differently for each univariate direction. It's a very general construction. It provides you a mesh from starting from 0. Exactly, you just have your knots that you have defined for introducing your B-splines, and you already have the mesh. Very nice. The idea, okay, till now we are approximating a square. Physical domains have different shapes. Okay? The idea is that the physical domain is mapped starting from a parametric domain by an isogeometric map. Okay? What is an isogeometric map? As we have seen for curves, okay, we can make a linear combination of the B-spline basis function with the contour points, and we get a curve in the space. In this way, if we use multivariate B-splines, we will get, for example, the shape of a surface or anything you want. It depends on how you move your contour points. It works exactly as for curves. Okay, then this is a map that goes from omega hat. Okay, sorry, I don't know. Okay, it goes from omega hat to omega, your physical domain, and the physical domain is exactly the image of this square, for example, in 2D. Nice. Usually the domains are, I told you, are B-splines or NURBS, okay? And the isogeometric NURBS, the idea is to use the same basis functions, like or B-splines or NURBS, that are used for the domain parameterization, okay? Then, very nice. the Bezier mesh, okay, in the physical domain will be simply the push forward with the isogeometric map of these parametric elements. Okay, so you just see an element k on the Bezier mesh of the physical domain is just pushing forward the element q in the parametric mesh. Okay, it's very simple. It's free. I mean, your mesh in the physical domain is totally free. As I was saying, there are some requests on this app because, as you know, for finite elements, when you have your reference triangular and you map it, you want something like shape regularity, someone like that, some properties like that. Otherwise, you will not approximate correctly or will not have good approximation results. Okay, and here we're asking some regularity too for your map. Practically speaking, we don't want the elements on the parametric Bezier mesh to collapse in bad stuffs. It's not required. So we are just asking f, of course, to be a B-Lipschitz homomorphism, but we want that in each singular element of the parametric Bezier mesh to be a diffeomorphism, so continuous, smooth, with smooth inverse. Okay. Very nice. This is an example. So far I talked about all these kind of constructions, but this is a visual example. You map this square into like a quarter of a ring in R2, okay? And see this element Q is mapped in this stored element K. Now the concept is very easy. We have defined two spaces, okay? The parametric one and the physical one. Usually, this one is given by software, like by CAD softwares. Sorry, and you have to define your basis upon this. Okay? How to do it? We have defined the multivariate basis upon this place. Okay, some other notations. Of course, HQ is the diameter of the element in the parametric mesh. H is the maximum of all these diameters. And HK wants to determine the diameter of the element in the Bezier mesh, in the physical domain. Okay? How to define the discrete scalar spaces, and so the basis that we will use on the physical domain. On the parametric domain, it's quite simple. As I told you, we have defined the multivariate B-splines and we use them. Okay? They are defined in 0, 1 for every direction, and so in the square for 2D, in the cube 0, 1 to the third for 3-dimensional spaces, and we call VH hat this the span of all these basis functions. Now, actually, I want to introduce the same space also on the physical domain, and the way to do it is by pullback. Okay. VH is simply the precomposition with the inverse of the isogeometric map of the B-splines basis functions that you have on the parametric domain. Okay? These techniques, it's nice and cool. It's standard. You use the pullback construction and you define VH, the space of all these basis functions that you have with the pullback of the isogeometric. Okay? So now we have built a space on the parametric domain and a discrete space on the physical domain. Very nice. Most of us deal with domains that are bounded, and maybe wants to deal with partial differential equation with boundary conditions. Okay? And if you want to add some conditions on the boundary, for example, homogeneous Dirichlet conditions, we just restrict, okay, the previous space, put in some new informations like your basis functions are 0 in a piece of the boundary. Okay, for this is a standard construction. Okay. Then what you need is also another assumptions here, because of course you don't want to to have bad boundaries, like just part of one edge or something like that. So we are just asking that the boundary of the domain is just simply mapped by the isogeometric map by the edges of the parametric domain, faces or edges or something like this. Okay. Let us show you an example. These are two basis functions. We have seen them all before in the parametric domain. If I use the pullback construction, okay, my isogeometric domain is this one, and the basis function just placed in the correct place of the physical domain. Okay, and they are exactly representing the same shapes that I needed. Okay, very nice. Okay, just one thing. If you want, you can interrupt me whenever you want. I never mentioned it. Okay, but if you have questions and want to ask it, do it. Don't worry. Very nice. How to apply this? Okay, we have built two discrete spaces. How to apply this to partial differential equations and numerical schemes? I took as an example the advection-diffusion-reaction equation. Okay, and the coefficients can be also space depending. In this case, nothing changes. This problem is well known in literature. For example, you have to ask that the term f, the map f, is in L2. The domain, for simplicity, I took all the boundary of the physical domain omega. And for me, it's a Dirichlet domain with homogeneous conditions. Okay. And okay, these are some regularities on all the coefficients of the partial differential equations. And these ellipticity conditions, it's quite enough to show that there is existence, uniqueness, and well-posedness of the problem. Okay, you have a bilinear form. You are in this context. You can define this bilinear form A, starting from the integrating your equation by parts and over omega, and finding the variational formulation later. These bilinear forms, thanks to the ellipticity condition, is coercive as soon as this condition is respected. Okay, and as I was saying, the space V0 gamma d for me is the variational space where we set our problem in weak formulation, in weak form, and it reads like that. Okay, A of u v, u is the solution we want to find, b is a test function in V0 gamma d. Okay, it's the homogeneous Dirichlet boundary space that is a subspace of H1. Okay, so are the H1 functions with the 0 value at the boundary. And it should be equal to the integral, so to the scalar product in the sense of L2 between f and your test function. Nice, as I already mentioned, existence, uniqueness, and stability, they all comes from Lax-Milgram lemma. Okay, and this is the continuous version weak problem. The discrete problem should be that you take the test functions, you are searching a solution UH, subscript H, in the isogeometric space I introduced before. And you are discretizing, of course, your equation, your test functions are in the same space, and this is how it reads the discrete problem, discrete formulation. And of course, Lax-Milgram provides you, again, solutions, existence, uniqueness, and also regularity, of course. What we know is, just a recap, we have this theorem, okay? We are simply, okay, how do you solve this? For example, perform a Galerkin method, as you do usually for finite elements, but you have now that your space is made of isogeometric functions, okay? So your solution will be, what's the point? Your solution will be already a B-splines or a NURBS curve or a surface, and you can reuse your solution exactly as it is given in CAD softwares in order to modify, for example, your domain again, because you want to perform a better simulation later. Okay, and okay, it works exactly like finite elements, but plus gives you this advantage, okay, that you have already computed your solution in the CAD software's language. And plus you have skipped the meshing process. The theorem states that okay, the error goes down as your usual for finite elements as the h, that is the mesh size, okay, yeah. And the order is q. The order it depends on the regularity of the solution. Where, if u is regular in hs plus 1, this q would be the minimum value between p, the polynomial degree you are using to discretize, or s, the regularity of the solution. So if your solution is not such regular, you can use higher order polynomials, but the error will not go down so fast as you are expecting. And it goes down just with h less. Very nice. This graphs reflects exactly this theorem, the statement of this theorem. They are taken from an introduction to numerical analysis of isogeometric methods by my supervisor Booth and Altera. What we have here is that, of course, the solution of this problem is regular in the experiments they provided, and it goes down exactly like the order p that we are expecting from the theorem. Okay? So this is in terms of the mesh, and this is in terms of the degrees of freedom, which are just simply the control points of your solution. Okay then. We have seen some standard way to proceed for introducing discrete spaces for discretizing your equations. It's a very well-known problem, the previous one. These are not so common, but are really recent projection, let us say, into discrete spaces. These are called, these projections I want to introduce are called quasi-interpolation projections, because okay, they do not interpolate the functions that you project, but they have good approximation properties, and they can still give you estimates of the kind like this previous one. Okay. Oh, I didn't spend any words on the proof of this one, but it's quite standard for who has seen some numerical methods for finite elements.
So using UCA, now we see the approximation property to put in CA.
Exactly. Okay. UCA, and if you find a good projection into the space, use it, and if it is stable with good approximation properties, then you're done.
And this projection is still conforming.
It's still conforming, yes.
And the constant C, I guess, like in element is the rate between coercivity and continuity.
Sure, you are using Cialema.
Okay.
You're using exactly Cialema, and that gives you exactly the same concept. The constant C actually, M9, because of course at the beginning is that of CA, but then since you want stability of the projection you will use in order to prove the theorem, it will depend on the constant of stability of your projection. I will arrive sooner to that part. Okay. As regards projections, okay, we need an assumption. We need some quasi-uniformity of the partitions. Okay, these are quite standard techniques, as I was mentioned before, in order to have shape regularity properties. Like this is exactly the reflected shape regularity condition for a PGR environment. Okay? Then, in the univariate case, imagine you have a function in R2 over 0, 1, and you want to project it in a discrete space. Okay? So, in the parametric case, we are still arguing with the parametric case. In the univariate, you define a projection simply by introducing a dual basis of your B-spline functions. Okay? These lambda I, j are dual bases. It means that simply evaluated over the basis functions, they give you the chronicle symbol. Okay? They are linear functionals that define it as you want in general. Okay? The point is, can we find some good dual basis that gives you nice properties and so on? This is nice if you have this property that you define these coefficients, okay, lambda IP evaluated on F as a dual basis, somehow you can reproduce the B-spline space. Okay? That whenever you apply the projection to a spline curve, you get exactly that spline curve. You don't change it. Okay, I found interesting from a draft by Lee, K. Morgan, a draft on B-spline curves. Okay, I found interesting this construction of these quasi-interpolant projections. They have a general algorithm that provides you any sort of projection that you want that has just some 3 steps, and it's a local projection because you find you first individualize an interval. Okay, you want to find a projection that is global, but then you restrict to a local interval. Of course, if you want to find the coefficient for the Bezier-spline function, the interval must intersect the support of that function. Otherwise, you are not using that spline function to interpolate or to approximate the function. Okay? So you have to be close to the support of that, intersecting it, and then you find a local method, and the local method is interpolation in my case. Okay, but you can use any local method you want, like mean squares method. I don't know. You can be as general as you want here. That's why this is a general construction. And then the global coefficient will be this Bj obtained, the jth one obtained by the local approximation method. Particularly for an example, for the quadratic and interpolation case, I need 3 points, okay, in order to interpolate with quadratic polynomials. And I fix 3 points in an interval that intersect the support of Bij. But the beauty is that if you are smart on choosing the 3 points, okay, for example, if you choose, remember the B-spline function of order due in the univariate case has 3 non-spans as supports. Okay? If you choose the inner element as your interpolating domain, you can fix the 3 nodes exactly in the extremal ones, in the extremal points, and the midpoint. Okay? This lets you solve it just once, this problem, and have an explicit formula that from which you can compute the Bj that you need without solving this system. Okay? The beauty of this is that if you fix correctly the points where you interpolate, you have an explicit formula to use. Very nice. I implemented this method, okay, not just for degree 2, but also for degree 3. You can do it for any degree polynomial you want. The formula that changes is this one, but as you can see, it depends only on the data you have. Okay? And the result is that this projection is stable, as we wanted, with a constant that does not depend on the mesh size, let's say, and the order is p plus 1, okay? At least for L2 estimates. So the best approximation you can do is bounded by a constant, h to the p plus 1, and of course the norm of the p plus 1 derivatives of the function that you are approximating. Very standard stability result. This is just an example. I was approximating a smooth function, I guess like the sinus of 10 pi x, something like that, I don't know. A lot of oscillations in the middle. And I was doing it with the degree 3 polynomial, degree 2 polynomials. And I get exactly, this is the empirical order I am this is the empirical order I'm getting, and this is the theoretical one I'm expecting, and it is exactly the same. So in the univariate case, they approximate with the order you want, and it's a good, so it's a good approximation of your functions. Very nice. Together with this projection, I found interesting some work from my supervisor, Annalisa Buffa from EPFL. She's working with these commutative projections in order to build these commutative diagrams. Remember, we had a projection from L2 to the spline space SP, I put it for H1 functions. I put it here in this graph. Okay. First of all, anybody of you is common with commutative diagrams? Okay. Quite a bit. Just a recap. We have two short sequences on the top and on the bottom. Okay, one on the top and one on the bottom. What does it mean? These arrows are just maps that links together the spaces that you see. R, as seen as the space of constant functions, okay, is isomorphic to that. H1 0 over 0, 1 is of course the one-ness over the space, H1, and L2 the Hilbert space. This arrow is the derivative with respect to the variable. Okay? The functions that are in H1, if you apply the derivative, of course you will get a function in L2. What does it mean 0 here? This means that this map is surjective. Okay? So that means the image of the derivative is exactly all the space L2. And the map R is just to say that, the space R is just to say that this arrow here is the simple inclusion inside the. We want to identify the constant functions with the constant numbers. Okay? And how do you read this line? This is an exact sequence, short sequence. That means that the image of the previous map, for example, the inclusion, is exactly the kernel of the following map. Okay? Of course, the derivative of constant functions is known. It's zero. The image is exactly the null space of the derivative map. And the same happens here, because if you think this as a trivial map that plots it all to 0, okay, that maps it all to 0, okay, of course, whenever you move here, and this map is surjective, of course, the kernel is all the space. Okay? Just you read it like that. The beauty is that if I put my quasi-interpolant projection here, I can ask to build another projection at this place, from L2 to another spline space. And if I choose SP minus 1 over this T with the non-subscript, overscript, how do you call it? Okay. Okay, if I choose this other knot vector, it's simply the knot vector for the derivative space. That is the one where we remove the very first one knot and the very last one. Okay? So it's exactly T, the knot vector T, without two knots, the very first one and the last one. And this pumps the derivative space of these kinds of functions. If I'm pretty good at defining this map, I can get a commutative diagram. That means that if I want to go from H1 to SP minus 1, I can choose this verse, this path, or this other one. Okay? This is the definition. Okay, we define this map this way when we deal without boundary conditions. When you deal with some other boundary conditions, you can ask different kinds, like, for example, preserving the mean of the function. By the way, if you are able to, you can define it in a smart way, and what you get is exactly what I was asking for, the commutativity of this diagram. That means that if I take a function f in H1, and I apply the derivative operator and project from L2 with this new projection, okay, I get exactly the same function in this space if I had chosen the lowest path. That is, first project your function into spline space and then apply the derivative operator in the discrete, restricted to the discrete spaces. Okay? Very nice. A little bit boring, but these are cool because, okay, these are all in the univariate case. As already seen for the basis functions, the projections for multivariate spaces are simply the tensor product of all the univariate projections, okay, that we define. We can put one commutative projection on one quasi-interpolant. You can choose whatever you want and with tensor-product construction your projection in the multivariate case. Okay? And of course, the coefficients will be themselves will be the tensor-product of the dual maps that you have used before. I don't know if you know about the RAM complexes. This is more geometric. Yeah, very nice. I don't have to spell many words, but by the way, no. These are all functional spaces. Okay. This one with the head is just to remind you. I call them x0, x up to x3. In order to say that they are the functional spaces over the parametric domain. Okay? Without the head, they are built over the physical domain. Okay, H1 is again subordinate space, L2 Hilbert space. These in the middle, these are H curl and H div. Sorry. These are curl functions in L2 with curl in L2. Okay, L2 to the D, because curl maps you into a vector space. Okay, and this other one is the space of functions in L2 with divergence in L2. The point is that in order to link these spaces, these functional spaces, okay, with together, the ones over the parametric and the physics domain, we can define these that are called Piola transformations, okay? And the point is that if you define it this way, you get another commutative diagram. It's called the RAM diagram, okay? The RAM complex. All this sequence here is exact, that is, again, the same game as before. The image is exactly the kernel of the following map for all the maps you see. And here you don't have just the derivative operator, but you have, of course, the gradient, the curl, and divergence operator. We are in the multivariate case. Okay? This is the setting in 3D, for example. These maps links the functional spaces below with the ones up, and all the graphs here commute. So again, you have the same property. Whether you follow this this path or this other one, you go from one space to another. Okay, and it is exactly the same. So as we have seen before, we can define B-spline spaces as tensor product over the parametric domain, and for each of the functional spaces I've introduced, you can define these sequence of B-spline spaces. Okay, the very first one choose the degrees you want for any univariate direction. The second one for discretizing H curl, you play a little bit with the derivative operator, so you choose p minus 1 for the first component of the vector map, p minus 2 for the second component, and p3 minus 3 for the third component. Okay, you make this choice. Let's say what you end for discretizing L2 with p minus 1 spline space, and if you link, thanks to the Piola transformation maps, these spaces in the discrete, okay, you can define. Well, you can define as pull back or push forward with the Piola transformations the discrete spaces over the physical domain. Okay? And thanks to the Piola transformation, also this diagram that is in the discrete spaces now commutes. What does it mean commutes for Piola transformation maps? That is that if you have some good properties like curve preserving, divergence preserving properties in the discrete, in the continuous case, you have found that Piola transformation preserves also for the physical domain, and now also for the discretization in the parametric and physical domains. So, for example, Stokes, okay, for Stokes I will use like the discretization for H div, and you have maybe if you are not familiar with Stokes, but maybe it is asked to have the divergence of the of the velocity map for the Stokes problem to be 0, and this is a property that you want to preserve, and thanks to these Piola transformations in the discretization, you already have it. Okay? Very nice. We are preserving properties of the derivatives operators. And the point is, how do I go from this complex that is in the continuous, so where I will formulate my weak formulation of the partial differential equation, to this one that is in the discrete, where I discretize my PDE. The point is that the projection in the parametric sense are simply the tensor product that I was showing you before of univariate projections. You can choose the commutative one, for example, or the quasi-interpolant ones. If you define it like that, I'm not reading it. If you define it like that, and use again the Piola transformation maps to get the push forward. No, see the push forward now in the physical space. You have for free the commutativity of this projection with the Piola transformation maps. That means you have built for the physical space a link between the functional spaces over the physical domain and the discrete ones, okay, with B-splines over the physical domain. And all this commutes, okay? So you can move from one space to another using the projection that you like, that is more suitable to you. Very nice. My master thesis work was focused on solving the wave equation with these techniques, with these isogeometric. Actually, I wanted to remind you the wave equation in this form with the divergent form because I wanted C to depend from the space. Okay? And as you can see, simply I'm putting some initial data and some Diminishing homogeneous boundary conditions on the boundary of my domain. Okay? As my domain, I will focus on the quarter of a ring that you have seen before. I rewrite this formulation, okay, this strong form, in a first order hyperbolic system. Okay? I perform a change of variables, and with this change of variable, what you get is these two coupled equations. Okay, this one is a vectorial equation, as you can see, for the velocity, and this one is for the pressure. Okay, I've introduced the pressure and velocity instead of the wave shape. This is the transformation of the initial data, of course, and the boundary conditions. And what I get is that I want to solve the vectorial equation weakly, okay? While I want to keep strongly in strong form the second model. Why? Because there is that divergence, and I know that the Piola transformation preserves divergences. Okay? So it sounds good to keep it strongly, because as soon as I discretize with the correct spaces, I already have the preservation of the properties of the divergence. Okay? And now I should discretize this formulation. Okay? But let me just tell you one more thing. We have energy conservation in these sections. The quantity of energy defined this way is preserved. You can simply see it. Just write the weak form of this one and use the correct S functions and sum together the equations. You get the preservation of energy. One little more point. I want to preserve energy. Okay? Because I have good properties on preserving divergence operator and so on. And in order to solve this evolution equation, I need a time-stepping method. And somehow, people have seen that energy somehow, for long-time simulation, it goes lost. Okay? And I would like to preserve energy too. Okay? What to do? My idea was to project the second equation into the discrete spaces using, actually, since the pressure is in L2 for me, in the setting of the continuous, I'm projecting it with the very right projection that you have seen in the diagram. So I'm projecting with this pi3 map, and using this projection doesn't mean that you are solving the same problem as before. So I'm not pretty sure that in theory I have energy conservation. So I would like to change a little bit also the first equations. And the way to do it is by imposing as a constraint the energy conservation. And what I get is that the first equation, the weak form, compares, well, it appears also this projection in the structure of the first equation. Okay? And so I have to compute also this projection when we solve. Okay? And in the discrete, I'm using a Crank-Nicolson time-stepping method because I have seen it is energy preserving. Okay? And so this is actually the problem I would like to solve. And the way is to solve this one and then update the pressure. Okay? Because I have all the constraint on the energy and the divergent preserving properties. This is an example. I started with this data. Okay, you can see anything, but believe me, there's a flow, velocity flow on this graph that defines the velocity as the initial state, while the pressure is 0. Okay, and after 1 second, the boundary is homogeneously Dirichlet. You see, I get this. If you imagine it as a membrane, it's like oscillating up and down. And what I get is that this is the shape of the solution of the, for example, in the color bar, you see the pressure, and okay, you will see, if you are so close, also the velocity field too. But the beauty is that I compared this technique to a standard Galerkin method. And what I get is that, of course, the initial error is like a little bit bigger. Okay? You see in the left and in the right the L infinity 2 or L2 norms. L infinity in time, that is, I take the absolute value and the maximum of the absolute values of the errors in time, and another L2 error measure in space. Okay? While these I'll take the L2, L2, both for space and time. What I get is, as I was expecting, they go down with the same order because I have good approximation maps and projections, and I have also the same order of convergence given by a Galerkin method. Okay? Because actually the difference is that in the beginning, the only thing that differs is that since I'm using different projection from the L2 projection, of course, for Galerkin, I will be the best approximation at the initial data. For my method, they would approximate the initial data correctly, but not as good as the L2 projection. Okay? Then the results are quite good, and it remains, so we have an alternative way of proceeding with local projection instead of L2, that is global projection. Okay? And this means that possibly in the future, it should be also analyzed the percentage of the parallelizable part of the code, okay, in order to be also maybe faster than the Galerkin method. And but in the very end, I want to show you the relative error in the energy evolution. The blue curve is the evolution of the relative error for a coarse speed discretization. Okay, like 0.2 as Nashville. Okay, and as you can see, not really, but this is 10 to the minus 12. Okay, so I'm performing 300 integer. I'm going up to t big T, that is 300 with 0.2. I'm performing about 1,500 steps with a Crank-Nicolson method. And the energy is still 10, the relative error of the energy is still 10 to the minus 12. That, in my opinion, is nice. But more interesting is the red one, because when I refine my mesh, or refine my discretization, what I get is that this is exactly the same simulation going up to 300 seconds, let's call it, but with 0.01 as a mesh width. And what I get is that I'm performing 30,000 steps with Crank-Nicholson, and I'm epsilon machina precision in the relative value of the energy. So I can say I don't lose energy with this method at all. And that's all for my part. I know it's a little bit strong because there are many concepts, but this is the project of 1 year, and I want to share you what I do. Hope you enjoyed it.
Okay, is there any question?
I have one.
Sure.
Which initial data did you take?
Which?
Initial data did you take for this assignment?
Okay, that's nice.
Right.
As I told you before, I wanted to use the coefficients that are space dependent. Okay? So I don't know closed form. Maybe using green there's a way, green formulas, but I didn't know any explicit solution in order to compare the error. Okay? So I had to build an overkill solution that is in a very fine mesh with a very standard technique, hierarchical, of course. What I did is using separation of variables. That's why you see membrane oscillations. Separation of variables and solving a Helmholtz type equation, but at eigenvalues. Okay, an eigenvalue problem of the Helmholtz type. So I computed the eigenvalues of the generalized Helmholtz equation. Okay, and that was the steady state that I used in order to go in time with a frequency that I know because I know the eigenvalue. Okay.
Yeah. What I'm wondering is, okay, these problems like web problems, they are difficult with Galerkin approach if you inject discontinuous initial data. Okay, if you take maybe something where it's discontinuous at the level of the derivatives, they can still work at least for Feynman Galerkin. So I'm also wondering how is that with B-spline.
Well, this is a path to follow because what I know for sure is that isogeometric techniques works well because you have a map. You can compute the space with the regularity that you want. So if you had discontinuous initial data, I'm expecting you would use maybe discontinuous spaces. Okay? And if you use continuous one, I'm expecting to lose something on the convergence rates. Okay? Because as you have seen for the advection diffusion regression, it depends on the solution of the regularity of the solution of the problem. So the order rate of convergence, it was the mean between the polynomial degree or the regularity of the solution. So I'm expecting to lose convergence.
No, that okay. It's just wondering if they work with.
Okay. But I never tried with this.
Yeah, because normally you take.
Because I wanted to see if I wanted to see if I can preserve energy. That's a very main point.
Thank you.
Okay, any other question?
Yes, I have a couple. So the first one would be when you say a standard Galerkin method, what do you mean? Because there are a lot of standard Galerkin methods.
Sure. Conforming Galerkin,
Conforming Galerkin. Have you tried to because what you did, the fact that you find this Durand complex and use this Durand complex to show the fact that you preserve energy reminds me a lot, and also the split thing that you did. Reminds me a lot of what you do when you try to solve this kind of equation with mixed finite elements.
Yes.
So you do the split link, you find certain type of elements that do have the same Durand complex, and then you prove something like that.
Exactly, that's the idea of the work.
This is a generalization.
This is a generalization. Do you know about Ramitimma?
Yes, the formula.
Okay, let me go back. Let me go back to this slide. Okay. Do you know something about Stokes' problem? The fact that not all the finite elements works. You have to couple them in order to satisfy the soup conditions, and not so easy.
And not all of them form a DRAM complex, actually.
Actually, exactly. That's also another point of view. Do you remind a little bit of how Rabietto map is made? Actually, you are using P1 and P0 polynomial.
Yes.
And you are discontinuous.
Yes.
Imagine in 2 dimensions, P1, P0.
Yeah.
So, in 2 dimensions, this place, this part of the complex, okay, will be discretized with this projection, okay, and the discrete space, I think it's written here, is this one, okay. So remove one because we are in 2D. So remove also the univariate, okay. So what you get is P1, P2 minus 1, and P1 minus 1, P2. Okay? If you use P1, P2 the same with P1 equals 0, for example, P1 equal 1, you are exactly doing Rabietto map, but in the isogeometric case. This works not only with P1, P0, this works.
You can increase the degree how much you want.
You can increase the degree. Sure. There are some.
And you don't need to design specific algebra.
No, because you have the complex and you put the degree that you want in the complex, and you are sure you are preserving the divergence. So the point is how to be sure to preserve the divergence. Maybe it's equal to 0. Okay, of the velocity per space.
So you achieve the Hierarchical map, and you achieve also the Bezier-Curve.
The?
Bezier-Curve.
I don't know.
Okay.
Be honest, I don't know. I just know these informations because I worked a little bit. I still didn't understand at all the complex at the beginning. So maybe still now I'm not understanding it very well.
No, I was just wondering, since you can retrieve the Hierarchical map, you might be able to retrieve as well the Bezier-Curve. Is another element that is.
Yes, I guess maybe there's a way. But as I was saying to you, I'm not ready to tell you yes or no. Okay?
And then another question that I had is actually, so when you impose that energy conservation, what you're doing is at the end of the day searching for a settled problem, right?
You are searching, you tell me?
For a settled problem, you're imposing like a Lagrangian multiplier.
I have never seen it that way. I have to think about it. The point is that for me, imposing energy is changing the problem. Because I already changed it when I wanted to use the gram complex, the ram complex, or the spline complex. So, if I'm changing the problem, I would like to pay another price to change also the previous equations, but in order to be sure to get the preservation of the energy. Okay? But I don't know, I can see in this context any Lagrange multipliers or okay? Maybe there's a sort of parallelism or extension to that.
And one last question, but
sure.
So all the problems that you've shown have been solved on very smooth domain, like the annulus, the circle, or this kind of thing. Let's say that I have like a non-smooth domain. Let's say, for example, a sector of the circle.
That's another point. Non-smooth domain, that means that your isogeometric map is not smooth. Okay? You will lose, since the B-spline bases on the physical domain are recomposition with the inverse of the map, you will lose regularity. So if you have a regularity,
That's of course, because you lose it as well as analytically, right? You have
okay.
the fact that you leave your solution leaves in 5/3, it's enough. Right?
Yes.
But did you try non-singular?
No.
Sorry,
No, I didn't try any particular domain that is non-singularities. But it's one of the next steps because actually I've presented you the Dirichlet boundary conditions, homogeneous ones. I've already worked also with the, how do you call that? Sorry, the periodic ones. For the quarter of the ring, using periodic ones means that I perform the simulation only on one quarter, and I would like to have the ones for all the ring. Okay? And in that context, when you link together two paths, okay, two patches, the correct name. Never show you about patches, but it doesn't matter. Few times already. You have problems of regularity when you join And that's one next step I would like to do, and so I didn't try that. Okay?
Thank you very much.
Okay, I believe we should stop with questions because otherwise we'll be.
Sure.
Okay.
I'm ready,
So maybe 5 minutes break and we resume. Maybe I will not. Let's start again. Sofia, now we talk about adaptive B-splines. So please.
Thank you very much. So now we go back to, we change setting, and from IGA we go to computer graphics again. One of the, we have, as Alen introduced you, the tensor-product B-splines, okay, has an extension to the multivariate case, the multivariate setting in general, for application, the bivariate setting of B-splines. However, tensor-product B-splines are not well suited when we wanna do a local refinement. So when we wanna work locally on our object. And this, you can see here, is due to the fact that when we insert we are not inserting only one degrees of freedom, only one basis function, as in the univariate case, but we are inserting as many basis functions as in the other parametric direction. So the number of basis functions grows really exponentially, and we suffer of the curse of dimension, and it's not very nice, of course. However, tensor-product B-splines, except for local control, still has all the other properties of the B-spline of the univariate case. So they are still kind of very strong, they are very good, but we really want to go local if possible. Over the years, there has been several approaches as an alternative to the tensor-product B-spline in order to extend the B-spline from the univariate to the bivariate case. Some are the T-splines, the partial hierarchical T-splines, the local refine splines, and in this talk we will focus on the last one, which are the THB splines, the truncated hierarchical B-splines. In particular, we recover locality thanks to the introduction of a refinement level L. So we build a hierarchy, and we have several levels, and this gives us the possibility to recover locality. So let's see how to construct this space. And I will introduce, we start by hierarchical B-splines, and later we will see what the T stands for. So first of all, we need a sequence of nested tensor-product spline spaces. So these meshes are all tensor-product B-spline spaces. And here it's more coarse, and then we go finer and finer. And it's important to see the relationship, the nestedness relationship, how it is. So V0 is included in V1, which is included in V2, and so on. And if you remember the not inserter procedure I introduced at the beginning of this course, in V1 we are able, thanks to nestedness, to represent all the functions which are also in V0 and V1. In addition, we need a sequence of nested closed subdomains. So omega is a subdomain of R2, sorry. And we take a nested sequence like that. So the inclusion, it's the other way around. So omega 0 is the biggest one, and then we go smaller and smaller. But here we will have this kind of function. we will see that on omega 0 we place some functions from V0. On omega 1 we take some function of V1, and now we have to see how to select. It has, of course, to be well-structured decision. So this is an example of the hierarchy. So this will be our final hierarchical mesh. And you can see that we are kind of gaining locality. So we are actually adding degrees of freedom only here, for example, only on the last level, and not everywhere. Actually, where we need it. That's the idea. So we start, that's an example in 1D, just to understand the construction and the definition of the hierarchical B-splines. So we start with a B-spline basis on our domain omega 0. And then we, I don't know if you see it in red, but we consider omega 1, or here it's L plus 1, so the following hierarchical level. And we consider the B-spline function whose support is not entirely contained in omega of level L plus 1. So we take the B-spline function of level L, so the previous level, whose support is not contained in the red region. So actually, this first one, this second one, this third one, because the support overlaps omega L plus 1, but it's not completely inside. And we discard the one whose support is completely inside. Then, on omega L plus 1, we consider the functions of the finer bases. So here we have actually more knots, so the spaces are nested. And of this basis function, we consider only some of them, which are the basis function whose support is inside omega L plus 1. And we discard the basis function whose support is not completely inside omega L plus 1. And so we combine these two levels in this hierarchical basis. So we take some of the coarse level and basis function and some of the final level, and we combine them in a new basis. This is done only for level N and level N plus 1. But of course, we do it for all the levels, and we collect all of them. And the space that all these functions together span is the hierarchical B-spline space. Here we gain locality. Still, there are non-negative functions, so we have non-negativity, but we lost partition of unity, which is a property of the B-splines we have seen. Also in the tensor-product B-splines, we have, for example, partition of unity. And here it is lost due to these too many overlaps here. You see, we have a lot of overlaps, so if we sum up here, we go farther than one. And that's what the T comes from, which is a truncation mechanism, in order to recover partition of unity, because it's a very important property, in particular for some fitting application we will see later, and also for the stability of our bases. So we consider, so we have, you remember we have a nested sequence of tensor-product B-spline space. So we consider, for example, VL and VL plus 1, and any function which is in VL, since because of nestedness, can be written as a function of VL plus 1. And we split the tensor-product basis function into sets, the one whose support is completely inside omega L plus 1, and the one whose support is not. And we define the truncation mechanism in this way. So considering, so we discard this first term of S. Okay, so of course we are not reproducing, we are truncating S. So we say, okay, in the expression of S, we don't take into account the basis function of level L+1, whose support is completely inside omega L+1. We discard them and we truncate this function. And this is the truncation of L at level L+1. Of course, we can truncate that, then it will be based on another function, let's call it F, and we can truncate it again and again and again. So we can always do this mechanism. Here there is an example. So the dashed line, it's another basis function, but let's say this is our S, this dashed line. And we can write this basis function as a combination of this other finite basis function on the background. And we truncate this. It means that we discard all the basis on the background whose support is inside omega, stressed in red. Okay, omega of the same level as +1, let's say. And so this is the truncation. And as I said, we can truncate it again. Applying this complete truncation, so we truncate function over all the hierarchical level that we have, and we get the truncated hierarchical B-spline basis. So we take our hierarchical basis and we just apply this truncation mechanism to all the elements of the basis. And that the fact is that the space, the B-spline space we get, is the same as the one of the hierarchical B-spline basis. So the truncated hierarchical B-spline are just another basis for the same space, and we recover the partition of unity. And we also have locality. That was also the starting point. Here there is some comparison. So, for example, HB splines on the first level, THB on the first level, HB on the second level, and you can see that thanks to truncation mechanism, the overlaps of the supports are way less, and that's what give us the partition of unity, and so on, also going further with levels. Furthermore, the THB spline give us the possibility to construct a so-called hierarchical quasi-interpolation operator. Alen already told you, for example, how to construct this quasi-interpolation operator in the tensor-product space. And the fact is that we can construct those quasi-interpolation operator for each level, because on the level, in our hierarchy, we have tensor-product B-splines. That's the key. So on each level, we have tensor-product B-splines. And so we can just, for each level, construct a quasi-interpolant operator of a function f. And then we can just build the hierarchical quasi-interpolant operator, taking our THB spline basis, and the coefficients which we need to associate to each basis functions are already there from the coefficients of the quasi-interpolant operator in the tensor product setting. Okay, so it's effortless because as soon as we have the one in the tensor product setting, we have for free the quasi-interpolant operator in the hierarchical setting. Okay. In particular, those are very nice, first of all because they are for free, and then because the coefficients can be computed in a tensor product setting, where we have seen that our basis has already a lot of nice properties. And as we see in our hierarchy, if we go local, if we add the tensor product only on a small part of our domain, we are not adding there too many degrees of freedom. So the degrees of freedom, the number of the degrees of freedom locally, it's contained. The problem is when you put a tensor product everywhere, and then it's too much. Locally, maybe you still have very few degrees of freedom, and so it's very easy to deal with. Thanks to the basis, those quasi-interpolants can be built in an adaptive way. Also in the hierarchical setting, we have the spline projection property, which Alen told us before. So let's see an application with the THB splines. And this is a geometric reverse engineering problem, which consists in the approximation of a point cloud. So we are given a point cloud, and we want to rebuild the underlying model. So in this case, it's a surface. Here we are dealing with scattered data. So as you see, they are scattered. There is no regularity in the data we are given in input, which are the F. So those are the data in the space. And here we should also set some parameters. So we have to parameterize this data. Here we assume that we know the parameterization. Maybe some neural network will arrive also for them. But so that's the problem. So we are given a set of scattered data, and we want to reconstruct this surface who is free from artifacts. For instance, these self-intersections I mentioned before. In applications, they don't have to be there. But at the same time, we really want a high precision models, so with a very, very little error, but whose computational cost is not too much, it's not too high, of course. And then we want a model which is compatible with a CAD or CAE, so computer-aided design or computer-aided engineering tools. That is, the software which are in the companies, which are based still nowadays on tensor-product B-splines. Okay, so if we build another model which is not dealing with tensor-product B-splines, of course, maybe some company won't use it because it's not compatible with their softwares, okay? And in order to solve this problem, then we can use THB splines, because thanks to the hierarchy, and since in each level we have tensor product, they are compatible with CAD and CAE softwares. And in order to create a model, we use a two-stage hierarchical quasi-interpolation algorithm in order to build our quasi-interpolant operator. So this is our quasi-interpolant operator, and this is the two-stage algorithm. So in the first stage, it consists in the computation of the coefficients. So we arrive at this stage that we have a THB basis. Okay, we have the basis, and we need to find the coefficients in order to approximate the point in input. And this first stage is characterized by two steps, which are the selection of a local data set, because if you remember, the B-splines have a local support. So in order to find the coefficients of a single basis function, we don't have to take into account all the points we have, because this basis function will see only a small part of them, because then it's zero everywhere else. So even if there are points, this basis function is not there anymore. So we have to select the local data, so a local data set for each basis function, and a local approximation of this local data that we have collected. The second stage consists in assemble this quasi-interpolant operator, and then to proceed with the adaptive scheme. That is, we compute the error we are making, and then we have to understand where and how to insert degrees of freedom. So, as regard the local approximation, our work that we have done consisted in a local spline least square with a smooth term approximation of this data set. And then we also define a refinement criterion in order to add degrees of freedom. So, here there is a recap of the first stage. I don't know if you can really see this image, but those are the parametrized points. And here we have a basis function in the parametric domain. For each basis function, you can see here we select a local data set for these basis functions. By instance, for example, here you don't see, but there are some dots inside each support. So it could be that for this we consider only the points inside the support. Could be that they are not enough, by the way, because as I said, those data are scattered data, so there is no structure, so there is no guarantee that there will be some point in the support of each basis function, for example. But still we need a coefficient for it. And here we compute a local approximation and we approximate those points in a tensor-product setting. Here we have a tensor-product approximation of this point, and for the corresponding basis function we extract exactly that coefficient that we put in our hierarchical setting. And this is what we have for free. So we compute the coefficient in a tensor-product setting and we have the coefficient for the hierarchical setting for free. I mean, it's the same. So here, I will go a little bit faster, but there are many ways we can collect local data. So this is the support of the basis function. We can make a circle, squares, or whatever we prefer. And then there are also some parameters to take into account to avoid artifacts. And those parameters, we will introduce them to avoid artifacts. For instance, here, I can tell you that here we got 3 points inside the basis support. And for the algorithm, they were enough to be fit, and they were fit with a plane. I mean, the solution is correct. But here we got this oscillation which we didn't want. So we just say, okay, 3 points are not enough. We want at least n min point, a minimum number of points to make this local fitting. And this wasn't, this solved our oscillations. Not always, because for example here we had for those for the basis function which were active here we had enough points, but we were all on a line. So they were enough, but on a line, so also here we had some weird oscillation, and we said, okay, don't take into account not only the number, but also the kind of distribution. Okay, so those are all tricks we needed to add. Here there is the first stage. As I mentioned briefly before, we implemented a spline approximation with a smoothing term, which is this thin plate energy. And the smoothing term, it's up to the user to set it. Okay, we just look at in the literature and we find that with some tensor-product B-spline, this smoothing term was used, so we implemented as well. And then there is the second stage. So far we have computed all the control points, and now in the second stage we assemble the quasi-interpolation operator, and then we compute the error we are committing using this model on the scattered data we have. In particular, if there are at least alpha points, so if there is a certain amount of points for which the error is too big, so it's above this threshold epsilon, then we decide to refine. Otherwise, if there are enough points for which the error is small, then the adaptive procedure stops. And this is it's done very common in companies, because this scatter data maybe scan data, so usually some noise is always there. So to ask for all the points to have a very small error, it could be that also it leads to not good solution at the very end, because we are kind of going very close to some noise, which we want to avoid. So we collect the points in the parametric space where the error is too big, and if we are enough, we are fine. And how we are fine? We just split the support of each marked function, which are like the basis function whose support overlaps these points. So if I have a point with a too high error, and there is a B-spline function with active, so whose support is overlapping this point, we decide to split its support in order to get finer basis function. Because there, locally, we are adding degrees of freedom. So this should bring us also a better resolution of this area. And here we don't really split. Also here we have to do it very carefully, because too many degrees of freedom again can lead to some oscillations. So we split the support only if there are inside, let's say, enough data. So if there are enough data inside the support of this basic function, we split its support. Otherwise, we keep it as it is. So this leads to an adaptive loop, which I will show you very quickly now. So let's say that this is our settings at the beginning. So we have a tensor-product, you see? So this is a tensor-product approximation. We compute the model, and then we evaluate it, and we search where the error is too big. So these red dots are the points where the register error is too big. It's above our threshold. And here, we refine. So you see, we add degrees of freedom really only where they are needed. Then, so we solve the problem, we estimate, we mark where the error is too big, and we refine. Then we start again, and that's the adaptive loop. Because now the basis is different. We have two levels in our hierarchy. So we change the basis, the model, it will change. So we solve again the problem, we estimate where the error is too big, we mark where to add the degrees of freedom, and then we refine. In conclusion, I would like to show you some results we got. And those are all approximation with THB splines on scattered data given to us from a company in Germany. And yeah, so here I just put the THB model because the tensor problem models is not even possible to get. It will be just too expensive. There will be just too many degrees of freedom. Okay, here we really have a lot of hierarchical levels. In the literature, you can compare this model with the other approximation, which are also local. But yeah, we proved that this was a little bit better. And you see, I mean, maybe this number didn't tell you a lot right now, but these 3,500 degrees of freedom are really way less than the number of degrees of freedom you get in the tensor-product environment. So we did this, that was a tensile. This is a blade. Those are all airplanes part, turbine, and parts. And here I think you can really see where the mesh, how the hierarchy is built. Here there is another one, that's an end wall. And then just briefly mentioning that we extend also these THB splines to closed surfaces. Let's say closed in only one parametric direction, so not completely closed. Yeah, and that was all. from me, and also from Alen and from on this morning session, and thank you very much.
So is there any question for Yes, please.
Thank you both for the presentation. I have, even though it was difficult to start, I wanted to know if there are any guarantees about the behavior of the gradient.
The gradient?
Yeah, like is it going to be oscillatory maybe, or is it going to behave?
I've never computed the gradient of the surface, but the idea is to have as much regularity as possible. So we want to preserve the basis. I mean, the basis regularity is kind of preserved also for this model.
Because your splines are super smooth.
Yeah, our splines are super smooth. I mean, not super, but depending on the degree smooth. Yeah.
Thank you.
Maybe I can answer the question you made me before, and I can mention that for the quasi-interpolant operator, it's also very nice because the coefficients can just be computed all in parallel, because all these tensor-product sectings are all independent from each other, so you just can do it all in parallel. So.
Okay, any other questions? Okay, let's thank both speakers then, and
Thank you very much
Sofia
for
for the nice mini course. And yeah, thank you very much.